Welcome back, everybody. Learning as a hobby here. In this video, I want to go over the summary for Section 1C in Sheldon Axler's book, Linear Algebra Done Right. So we'll jump right into my summary here. Let me bring up my notes. All right, so here we go. Section 1C is on subspaces. So oddly enough, we start with the definition of a subspace. All right, so here's the definition. A subset U of V, where here V is understood to be a vector space. A subset U of V is called a subspace of V if U is also a vector space using the same addition and scalar multiplication as on V. And he gives us a simple example of a subspace here. This is a subspace of F3, meaning the set of all three tuples of numbers from a field. So, the first two components can be anything, and the third component is 0. So you can check that this is a subspace. It's a vector space in its own right, meaning that it satisfies all of the vector space axioms, all 8 of them, if you use the vector space operations from F3. I won't go through that because we already went through verifying vector space axioms, so I'll skip that, but you can verify yourself that that is a subspace. Now, if you're verifying that something is a subspace, you don't actually have to do all that work. You can, because a lot of the stuff from the vector space axioms are satisfied by the fact that they come already from a vector space. So here, if you want to show that something is a subspace, actually, all you really have to do is show these three things. So he gives us the conditions here. So a subset U of V is a subspace of V if and only if U satisfies the following three conditions. All right, it has to have the additive identity. It has to be closed under addition, meaning if you take two vectors from the subset and add them together, the sum should also be an element of the set. And it also has to be closed under scalar multiplication, meaning if you take an arbitrary scalar and an arbitrary vector from the subset, if you take the scalar multiple AU, that should still give you a vector in the subset. That's what they mean by closed, right? And then just a proof of this. Since U is a subspace, the three conditions hold by definition because it's it's a vector space, so it has to be closed under the operations, and the 0 vector has to be in there. That's just comes from the vector, the fact that it's a vector space, right? It's meaning it already satisfies the vector space axioms. All right. The other going in the other direction, if the three conditions hold, then U contains an additive identity. All right, that's because that's one of the conditions, right? The first one. So it has an additive identity. By closure under the vector space operations, if U is an element of U, then negative U, or meaning the additive inverse of U, is equal to -1 times U, which is an element of U, right? Because it's closed under scalar multiples. Therefore, every vector in U has an additive inverse, and all the other axioms hold, again, like I said a second ago, because the vectors already come from a vector space. So that proves that these conditions are sufficient. So if you want to prove that something is a subspace, then all you have to do is show that it satisfies these three conditions. Okay, he gives some examples here, and I didn't do these out in detail just because they're relatively straightforward, but I did do some of the details, so I'll show you that. He doesn't actually do these examples in the book, but you should try them yourself. There's a few examples he gives here. So let's go through them one at a time. So the first one says, part A, example A, says if B is an element of the field F, then this 4-tuple of numbers where x3 is 5x4 plus b, x4 is the fourth component in the 4-tuple, and x3 is the third component in the 4-tuple. So this set is a subspace of F4 if and only if B is 0. So before we get to the other ones, let's actually look at that. So here I did it both ways because it's if and only if. It's by conditional. So here we go. So starting with assuming that B is 0, then S looks like this. It's the set of all 4 tuples that look like this, where the first and second component can be anything, and same thing for the fourth component, but the third component has to be 5 times the fourth component, right? Because B is 0. So obviously the zero vector is in there since, if you take x1 equals x2 equals x4, you get the zero vector. And the zero is obviously 5 times 0 in the field, so that works. So the zero vector isn't in the set. Number two, if you take two arbitrary vectors from the set, so the first one looks like this, the second one looks like this, and you add them together and simplify, you get the same structure that you want the vector to look like. So it satisfies the condition for membership in the set. In other words, if you look at the third component, it's 5 times the fourth component. Right, and same thing for condition 3. If you take an arbitrary scalar from your field, here I'm calling it alpha, and take an arbitrary vector from the set, then when you scale and multiply, again, the condition holds. The third component is 5 times the fourth component. So the three conditions are satisfied, therefore it's a subspace, right? And then to show that it doesn't work if B is not 0, then showing that here. So if S is a subspace, then, for example, if x1, x2, x3, sorry, x1, x2, x4 is 0, then you get the vector 0, 0, b 0. If you add that to itself, in order for it to be a subspace, that sum of vectors has to also be an element of the set, right? Because it has to be closed under addition. But if you take the sum of 0, 0, b 0 with itself, you get 0, 0, 2, b 0. And that is in the set S only if 2b is equal to 5 times 0 plus b, or in other words 2b equals b, or in other words b equals 0, right? So that shows that this is true in part A, right? Part B says the set of continuous real valued functions on the interval from 0 to 1, including the endpoints of the closed interval, is a subspace of R 0 to the 0. I don't know how to say it, but the space of continuous real valued functions from 0, 1 to the real numbers. We want to show that that's a subspace of sorry, the set of continuous real valued functions on the interval. Sorry, I'm not saying this great. Let me parse this a little bit better. The set, we want to show that this set, of continuous real valued functions on the interval from the compact interval from 0 to 1 is a subspace of this space. If you remember, the space here this is the set of functions. They don't necessarily have to be continuous. This is a set of functions f, where f goes from 0, 1 to r. Right, that's what that set represents. This is our vector space. You can show that that's a vector space, and we want to show that this set is a subspace. All right, so just scrolling down. Okay, so this one's very straightforward. From calculus, we know that sums and products of continuous functions are continuous. Therefore, that property holds for functions whose domain is the compact interval from 0 to 1. And also the zero vector is continuous on 0 to 1, so therefore it's a subspace that satisfies the three conditions. So, straightforward. Part C also is very similar to B, so I didn't really work that out in detail, just so you can see what part C says. The set of differentiable real valued functions on R is a subspace of R to the R. This is the set of real valued functions. This set here, this set here is the set of functions f such that f goes from R to R. All right, so this is our vector space V, and the subspace here is the set of differentiable real valued functions on R. So again, this follows because, for example, the function that is identically 0 is differentiable, infinitely differentiable, so it's in that set. And also the set of differentiable functions are closed under addition and scale multiplication, which you learned in Calc 1, so that is a subspace. All right, let's see. Example D, the set of differentiable real valued functions f on the interval from 0 to 3. This is the open interval from 0 to 3, such that f prime of 2 is equal to b is a subspace of r to the 0, 3. Again, that hopefully now you know what that set means. If and only if b is 0, this is going to be very similar to part A. Um, so here, like I said, similar to part A. So I'm not, in other words, I skipped, showing that it's a subspace because of, we know that it satisfies those three conditions from calculus. But here, just to show that it's a subspace if and only if B is 0. So in other words, f prime of 2 we want to be 0 and g prime of 2 we want to be 0 if f and g are in the set. If f is in the set, then f prime of 2 is B. If g is in the set, g prime of 2 is b. If we add them together, we get another function, f plus g prime, right? Because remember, derivatives add in that way. They're linear. The derivative is a linear operator, which we haven't really talked about yet, but you should know that fact from calculus. So f prime of 2 plus g prime of 2 is b plus b, which is 2b, and f plus g prime of 2 is b. Therefore, 2b equals b, which means that b has to be 0. Okay, and then the last example, part E. The set of all sequences of complex numbers with limit 0 is a subspace of C infinity. In other words, this set here, C infinity, is the set of, whoops, this is the set of infinite sequences of complex numbers. So we want to show that that's the set of all sequences of complex numbers with limit 0. We want to show that that's a subspace of that vector space. All right, so going down here to part E, I'm just showing that it satisfies the three conditions. So the infinite sequence of complex numbers that, all the entries are 0 is obviously has limit 0, so that's in the set. And if the sequence an and bn are in the set, then their limits go to zeros and goes to infinity. And if you take the sum of the nth terms for those sequences and use that as the nth term for your new sequence, if you take the limit of that, so here I'm calling it Cn, take the limit as n goes to infinity. Remember that limits distribute over sums, so that's the same thing as limit an plus limit bn, and we already know that that's 0 plus 0, which is 0. Therefore, the sum is in the sequence. Sorry, the sum is in the set, so it's closed under addition, and similar thing for being closed under multiplication. I'm just using limit laws there. All right, so that shows that that's a subspace of C infinity. Right, we have another definition next. Suppose U1 through UM are subsets of V. The sum of U1 through UM, which is denoted like this, U1 plus dot 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 plus UM. So it includes all the other subspaces in between. Is a set of all possible sums of elements U1 through UM. More precisely, U1 plus dot 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 plus UM is defined this way. So it's the set of vectors that can be written in the form U1 plus all the way up to UM, where each of the vectors in the sum come from the respective vector subspaces. So the little vector U1 has to come from the subspace U1, U2 has to come from the subspace U2, and so on all the way up to the vector UM has to come from the subspace UM. All right, so we call that the sum of those subspaces. Right, and then again he gives an example here. So if we have the subspace that he's defining here, U, which looks like this, it's a set of all three tuples of elements from a field F, where the second and third components are 0. The first component can be anything, and then W is the subspace where the first and third components are 0, and the second component could be anything. If you take the sum, you get the set of vectors that have third component 0 and the first two can be anything. Right, that's the sum of those vector spaces. Right, and then just another example of a sum of vector spaces. So you just add add these two together, and you get this sorry, we haven't proven that it's a subspace yet, but we get the sum. So that's what it looks like. All right, here's theorem. Suppose U1 through UM are subspaces of V, then U1 plus ... up to UM is the smallest subspace of V containing U1 through UM. Oh, so actually, I should say, just because I talked about subspaces up here a second ago, the definition of sum doesn't necessarily mean that U1 through UM have to be subspaces. They could just be arbitrary subsets, but in that case, the sum will not likely be a subspace. So, but here the theorem says if U1 through UM are subspaces, then the sum is a subspace, right? And in fact, it's the smallest subspace of V containing all of those subspaces. So here's the proof. So since UJ is a subspace, that means that the additive identity is in all of them, right? Because the zero vector has to be in the set if it's a subspace. Also, if alpha and beta are arbitrary scalars from the field F, and x prime are arbitrary vectors from the sum U1 through UM, then if you take the linear combination alpha x plus beta x prime, that's equal to alpha times U1 plus ... up to UM plus beta times U1 prime plus ... up to UM prime, and then you just rearrange things using the algebraic rules for vector operations, and you get this this new sum here. So you have alpha U1 plus beta U1 prime all the way up to alpha UM plus beta UM prime. And each of those terms in the sum are elements from the vector from the subspaces U1 through UM in the prescribed way for a sum of vectors. So for a sum of subsets, which means that it's an element of the sum. So U1 plus ... up to UM. Okay, so it's closed under linear combinations, so it's a subspace. Lastly, the sum U1 through UM contains each of the individual subspaces UJ for all J1 through M, since you could write any vector in one of the subspaces as U plus, and then all the take all the other terms in the sum to be the zero vector. So U1 plus UM contains each subspace U1 through UM as well. And if you assume that W is the smallest subspace containing those subspaces U1 through UM, then obviously W is a subset of the sum because the sum contains all of those things, right? It is also a subspace containing all of those subspaces. And lastly, if you take an arbitrary vector from the sum U1 through U plus ... up to UM, then U1 plus ... up to UM has to be an element of W because W is a subspace. Therefore, it has to be closed under addition, and et cetera, et cetera. So, it contains all of those vectors U1 and all the way up to UM. So, since UJ is, that's what I'm saying here, since UJ is in W for all J1 through M, and W is a subspace, therefore U1 plus ... up to UM is a subset of W, therefore W equals the sum, right? So that this sum here is the smallest subspace that satisfies that condition. Okay, definition. Here we want to define what a direct sum is. So suppose U1 through UM are subspaces of V. The sum U1 through UM is called a direct sum if each element of U1 plus ... up to UM can be written in only one way as a sum U1 plus ... UM, where each UJ is an element of UJ. In a way, you can think of direct sum as being like analogous to like disjoint sets in set theory, or it's like the closest you can get to disjoint subspaces in a vector space. You can never get subspaces that are disjoint in a subspace, and that's because each of them has to have the additive identity in it. So it's sort of like you're adding subspaces together that are sort of like the closest that they can be to disjoint. And the reason that we care about that is because you get unique representations as of sums of vectors in there. So, and then there's some, he's just going over the notation here. So if U1 through UM is a direct sum, then we use this special symbol for direct sum. It's an addition sign, but with a circle around it, right? And then we have an example of some direct sums here. So if U is this subspace here, it's the set of three tuples where the third component is 0, and W is the subspace where the first and second components are 0. Then F3 itself is a direct sum of U and W, which he says we should verify. So I didn't actually do that on the Jamboard here, but I'll do it on the whiteboard just because it's easy to show. Let me bring up the whiteboard here. All right, so U is this subspace X, Y, and F, and V is this subspace of F3. Oh, sorry, I think he called it W. W is this set of three tuples. And our vector space V is F3, which, if you've forgotten, is the set of all three tuples. Let's say A, B, C, where A, B, C are elements of F. All right, so we want to show that U plus W, direct sum U plus W is equal to F3. So first we have to show that this is a direct sum, and then we want to show that it gives you everything in F3. I'll do the second thing first, just because that one is pretty straightforward. So this will be the proof. So take an arbitrary vector in F3. Right, then choose AB0 in U and 00C in W. Then ABC is equal to AB0 plus 00C, which is so this is in U plus W, right? Okay, so that shows that F3 equals U plus W. So all we have to show now is that the sum is not just a sum, it's a direct sum. So we have to show that the representations are unique. So assume AB 0 plus 00C equals A prime B prime 0 plus 0C prime, right? Then that implies A minus A prime, B minus B prime, C minus C prime is the 0 vector, which implies A minus A prime is 0, B minus B prime equals 0, and C plus C prime minus C prime is 0. Where's the eraser? Right, which implies that A equals A prime, B equals B prime, C equals C prime. So we get uniqueness. So that shows that F3 is the direct sum of U and W. All right, going back to the notes now. All right, he also gives another example, which is analogous to the one we just did, except the subspaces are more sort of I don't know what's the word. It's sort of broken up component wise, I guess you can think of it. So if uj is the subspace x times ej hat in Fn, ej hat is, let's say, let me show you a couple of them. So E1, let's say these are in F3 just for the sake of concreteness. E1 would be the vector 1, 0, 0. E2 hat would be the vector 0, 1, 0. Oops. And E3 hat would be 0, 0, 1, etc. So if it's Fn, then you have n of these vectors. It's just the ej hat is just the vector that has 1 in the jth component and 0 everywhere else. So this set here is actually I don't know why I'm erasing this right now, but he's saying that this set here is Fn is a direct sum of those subspaces. The proof is very similar to what we just did, so I'll skip it. You would prove it in almost an identical way, except you're doing it for a general n instead of a specific example like we just did. So I'll skip actually doing that verification, but you should try it, especially if you haven't seen direct sums before. Okay, so here he gives us another example. Here U1 he's defining as this subspace of F3, U2 is this subspace, U3 is this subspace, and we want to show that U1 plus U2 plus U3 is not a direct sum. So all I have to do is show that you don't get unique representation of every vector in F3. So that's what I did here. So for any for any ABC, you can write any vector in F3, ABC, as a sum of vectors from U1, U2, and U3, which actually I'm doing down here. So if ABC is a vector from F3, then you can write it as A comma B0 plus 0, 0, C, 0 comma 0 comma C plus 0, 0, 0. And notice this is in here, this is in here, and this is in here. That means that F3 is equal to that sum. However, if you look at the 0 vector, you can obviously write it as the sum of the zero vector itself with itself 3 times. But notice you can also write it as this sum here. The sum of the vectors 0, 1, 0 plus 0, 0, 1 plus 0, minus 1, minus 1. Therefore, the 0 vector cannot be written, it can be written in more than one way. Therefore, representations are not unique, so this is not a direct sum. And that's all you need to show. Okay, another theorem here, theorem 1.44. Suppose U1 through UM are subspaces of V, then U1 through UM is a direct sum if and only if the only way to write 0 as, sorry, this should be the 0 vector here. Let me just fix that. The only way to write, the 0 vector as a sum U1 through UM, where each UJ is in the subspace UJ, is by taking each vector UJ to be the 0 vector. All right, so that's a theorem. Let's prove it. The forward direction is easy. If U1 plus U1 through UM is a direct sum, then obviously 0 has unique representation. That's the definition of a direct sum. Okay. Going in the other direction, let 0 have unique representation in the sum. Consider U1 through UM equals W1 plus WM in the sum. Then that means you can write the 0 vector as U1 minus, sorry, there should be an arrow on top of W1 here. Then you can write the 0 vector as U1 minus W1 plus U2 minus W2 all the way up to UM minus WM. And that means that UJ minus WJ has to be the 0 vector. Therefore, UJ is a direct sum, okay, because UJ is WJ for all J. In other words, you get unique representation for the you get unique representation for all of the vectors in the sum. All right, so I think this is the last theorem. Okay, theorem 1.45. Suppose U and W are subspaces of V, then U plus W is a direct sum if and only if U intersect W is the zero vector, the set containing the zero vector. So like I said, this is sort of showing in a way that direct sums are similar to like or it's like sort of like as close as you can get to disjoint sets, but you can't ever get rid of the zero vector because then it won't be a subspace anymore. Right, so all subspaces have to contain the zero vector, so when you take the intersection of any of them, at least the zero vector will be in the intersection. All right, so here's the proof. Let U plus W be a direct sum, and let U, W be vectors in the intersection of them. Of the U and W, I mean, such that U plus W is the zero vector, then that means that U equals W equals the zero vector, since U plus W is we assumed was a direct sum. So therefore the intersection has to be just a zero vector, right? And going the other way, let U intersect W equal just the set containing the zero vector, and let U be a vector in an arbitrary vector in U, W an arbitrary vector in W, such that U plus W equals the zero vector. That means that U has to equal the additive inverse of W, which means that U and W have to be elements of the subspace U because it's a subspace, and also that means that U, W have to be elements of W again because it's a subspace, which means that U and W have to be elements of the intersection. Then that means that, and that follows because U and intersect W is also a subspace. Then U equals W equals the zero vector, so U plus W is a direct sum. All right, so that shows that this, if you have two subspaces that are satisfy this condition, then it's a direct sum. He does give a little bit of a warning here, though. In the case of a direct sum of more than two subspaces, it is not enough for the pairwise intersection to be just the set containing the zero vector. For example, in the one that we did above a minute ago, U1 intersect U2 equals U1 intersect U3 equals U2 intersect U3, with all of those are just the set containing the zero vector, but U1 plus U2 plus U3, if you remember, was not a direct sum. So he's referring to this example that we did a minute ago. Where did we do it? This one here. So this example is the one that he's talking about. All right, so if you have more than two subspaces, then this condition is not enough. So this theorem here, you got to be careful to apply it only in situations where it applies, which is when you have only two subspaces, right? Then if you show this, then it's a direct sum. If you have more than two subspaces, then you have more work to do to show that it's a direct sum. Okay, so that is section 1C, relatively short section. Let me stop the screen share for a second. Relatively short section, and I do have all the exercises done for this section, but I haven't had a chance to write them up on the Google Jamboards yet, which I will hopefully be able to do today and maybe post the video for that tonight. I hope I'll be able to get that done. This way I can move back to actually I want to finish Simmons, and then I'm going to finish not finish Simmons. I mean finish chapter 1 in Simmons. And then I'll finish chapter 1 in Schifrin, and then we'll get back to Spivak, because if you recall, my last vlog, I said I want to push through, finish chapter 1 in all the books at least before I get back to Spivak. So, all right, guys, I'm gonna get some lunch, and then maybe I'll see if I have time to write up the solutions for section 1C in linear algebra done right, and then if I have time I'll post the video for that today. I'm hoping to get that done, so I'll see you in the next video. Until then, keep learning, everyone, and I know this is annoying, but if you do like this content, please like and subscribe, hit the bell if you want to get notifications when I post a new video, and I'll see you guys in the next video. So have a great day, everyone.